Hello, in this video we're going to talk about uniformly Cauchy. When we talked about convergence sequences, we built a criterion that shows a function is convergent, and that criterion was being Cauchy. We showed that a sequence is convergent if and only if it is Cauchy. So here we are going to show that a sequence is uniformly convergent if and only if it is uniformly Cauchy. So first, what is uniformly Cauchy? So the definition is quite similar to Cauchy. The only difference is the inequality of fn of x minus fm of x less than epsilon must hold for every x, not for a given x. So the statement is this: a sequence of functions fn from D to R is called uniformly Cauchy if for every epsilon positive there is a capital N such that for every n and m greater than or equal to n, for every x in D, fn of x minus fm of x is less than epsilon. Okay, so the key theorem that we're going to prove today in this video is the Weierstrass uniform convergence criterion. So what is the Weierstrass uniform convergence criterion? It tells you that if n from D to R, this sequence of functions is uniformly convergent if and only if it is uniformly Cauchy. So let's assume that it is uniformly convergent. So suppose fn converges to f uniformly. Let epsilon be positive. So by definition, there is some capital N in N such that for every n and m greater than or equal to n, and for every x in D, the difference of fn of x and f of x is less than epsilon. Now, if you take m and n greater than or equal to n, then the difference between fn of x and fm of x is less than or equal to fn of x, this is triangular inequality, minus f of x plus f of x minus fm of x. Each one of these is less than epsilon because n and m are both greater than or equal to capital N. So I would like this to end up being epsilon. It ended up being 2 epsilon. So we're going to go ahead and change the initial statement into epsilon over 2, and this would give us epsilon. And this means fn is uniformly Cauchy. Okay, so this proves the forward direction, which is the easier direction. The backwards direction assumes that fn is uniformly Cauchy. So suppose fn is uniformly Cauchy. And we would like to prove that in fact it converges to some function uniformly. First of all, we have to define that function. So that's the first step. And then we can show that in fact the convergence is uniform. So one thing that we know is that each one of the sequences fn of x is going to be Cauchy. So let x be in D. So by assumption, there is some by assumption, for every epsilon positive, there is some natural number n such that for every n and m greater than or equal to n, for fn of x minus fm of x is less than epsilon. So this means the sequence of numbers fn of x is Cauchy. So fix your x. Fn of x would be a Cauchy sequence. So by a theorem, we know that all sequences that are Cauchy are also convergent. By a theorem, Fn of x converges. So define f from D to R by f of x. This would be the limit. It's just basically the pointwise limit of Fn of x as n approaches infinity. Now we will prove convergence is not only pointwise, but it is uniform. So how do we prove this convergence is uniform? What we're going to do is we're going to take the fact that the convergence, sequence Fn is uniformly Cauchy. So let epsilon be positive. Since Fn is uniformly Cauchy, there is some capital N in N such that, or I'm going to call this maybe capital M, just so we don't mix this up with what we had before, such that for every maybe K and L greater than or equal to M, the difference between F, and for every X in D, the difference between Fk of X and Fl of X is less than epsilon. Now, I would like this to be the difference between Fk of X and F of X. So what I'm gonna do is I'm gonna allow this to go, L to go to infinity. So let's rewrite this. This would be Fk of X minus Fl of X less than or equal to epsilon greater than or equal to negative epsilon. Now, take the limit as L approaches infinity. So we obtain negative epsilon less than or equal to, well, this is less than, so it's strict, less than or equal to Fk of X minus, since I'm taking limit, the inequality becomes less than or equal to minus F of X, and this is less than or equal to epsilon. And this means absolute value of Fk of X minus F of X is less than or equal to epsilon. However, I was hoping to get to less than epsilon rather than less than or equal to epsilon. So I'm going to have to make some small changes. So I will change the epsilon at the beginning to epsilon over 2. This becomes epsilon over 2. This becomes epsilon over 2. This is epsilon over 2, which is less than epsilon. And since I have that, that means Fk converges uniformly to the sequence F. Okay, so in order to show a sequence of functions is uniformly convergent, we need to show it is uniformly Cauchy. Okay, so let's look at one example. So we looked at the sequence of functions Fn of X from negative 2 to 2 to R. If you look at this Fn of X, so suppose n is greater than or equal to m and epsilon is positive. So let's take that. Let's take the difference between Fn of X and Fm of X. This difference is the sum x to the k goes from, so the first one is k goes from 1 to n, the second one is from 1 to m, so the difference would be from m plus 1 to n, k squared 3 to the power of k. Now, this expression is less than or equal to, I can replace all of the values of x by 2 because the absolute value of x is less than or equal to 2. So first I'm going to use triangle inequality, k squared 3 to the power of k, which is less than or equal to the sum 2 to the power of k, k squared 3 to the power of k. K equals n plus 1 to n. Now if you look at this sum, I would have to show that this can be made small. So here's now what we're going to do. We're going to say this is less than, so note that the expression 2 to the k over k squared times 3 to the k is less than 2/3 to the k. And of course it's positive. Since the sum of 2/3 to the k converges, because it's a geometric sum, we can compare that with this one. So by the comparison test, the sum 2 to the k over k squared 3 to the k also converges. So since this series converges by the Cauchy Convergence Criterion for series, there is some capital N such that for every n greater than or equal to m greater than or equal to n, the sum of 2 to the k over k squared times 3 to the k, k from m to n is less than epsilon. So now this guy is basically the same thing that we had over there. So thus, if you look at the difference between fn of x and fm of x, that becomes less than epsilon if n is greater than or equal to m, greater than or equal to let me call that n1. For every x in the interval from -2 to 2. Therefore, fn is uniformly, so it's going to be uniformly Cauchy, and since it is uniformly Cauchy, it converges uniformly. So it's uniformly convergent. Now, what is the limit? Limit of fn of x as n approaches infinity is the limit as n approaches infinity of the sum x to the k over k squared 3 to the k, k equals 0 to n. And this by definition is the infinite sum. K equals, so it's from 1 to n. By definition, this is from 1 to infinity. X to the k over k squared 3 to the k. And thus, fn uniformly converges to this pointwise limit. X to the k over k squared 3 to the k. And this brings me to the end of this video, because that's exactly what they ask us to prove. Okay, and this is over the interval -2 to 2. Okay, great. So I will see you in the next video.